So we've set up our assumption about what kind of arrays our algorithm is likely to see. We're saying that most likely, right, with probability PU, we'll have unique elements and we'll have a quadratic running time. But we'll say that also there's some chance, PL, that we'll have a linear running time, and there's some chance that we'll have a constant running time. Right? These things we're all saying are possible, and then we're going to try to derive the average case running time as a function of PU, PL, and PC. Okay? So let's think about what we might actually run into, and let's try to predict maybe what kind of running time we'll see. So let's think about the space of all inputs as looking like this. So here's our space of all possible input arrays. And what we're saying is we've divided these into three classes, right? There's a PU fraction have unique elements, right? And have quadratic running time. So this is our big theta of n squared. A PL fraction have a linear running time. And a PC fraction have a constant running time. So the question we might ask is, how do different proportions of these impact the average case running time? You know, if you just took a dart and threw it at this Venn diagram thing, kind of, you know, what would you expect to see on average is part of the question we'd like to ask. So first, let's think about what happens if our space of inputs really looks like this, right? So what if our space of inputs, it has almost all unique elements, and then has a, you know, let's say some linear time inputs, and then some very tiny sliver of constant time inputs. You know, this is probably reasonable. There's probably very few inputs that run in constant time. The only way this is really going to happen is if your first element is equal to some other element in the array, and that other element in the array has some guarantee of being early, right? Constant time inputs are going to be pretty unlikely. Most often they'll be unlikely for this. So in this case, if the vast majority of our elements have a worst case running time, then our conjecture would be that the average case running time matches the worst case running time, right? Our conjecture is that the T average of n is big theta of n squared, right? Because, I mean, just according to the picture, we've said most of our inputs have an n squared running time. And n squared is quite a bit bigger than n, and so we would expect the n squared to dominate, right? So what about something more interesting? What about something that's less obvious? Something like this, right? What if a very tiny fraction, and I'll leave this to you to figure out what would actually generate such a space of inputs, but what if a very tiny fraction was PU? Right? Only a very small fraction of our inputs had a quadratic running time, and only a very small fraction had a linear running time, and almost all of our inputs had a constant running time. Right? What would we expect to see there? Right? So our question is, what is average here? All right, and so now what we're going to do is we're going to analyze this case. We're going to say, let's try to figure out what the average case running time would actually be if the vast majority of our inputs had a constant running time and only a small fraction had a quadratic running time. Because this piece is fairly obvious. And we know, by the way, we know that the average case running time can never be worse than n squared, right? So this side, where the answer looks obvious, and the answer is, well, average is just equal to worst, this side is less interesting to analyze. And what we should do is we should actually start here, right? We should start here. Why? Because suppose I get the answer on the right-hand side, the average case running time is worst case. Well, if that's the answer, then I guarantee that the average case running time on the left is worst case, because it can only be worse. But then we would have saved the time and not had to analyze the thing on the left. So let's take a look at this thing on the right and try to analyze what would the average case running time be over here. All right, so recall our formula. So the T average of n is equal to the sum of all arrays in the input space of PA times the running time associated with that input. Okay, so this is the formula that I presented earlier. And so now what I've done is I've essentially broken our input space into 3 different classes, right? So I've got my PU, my PL, and my PC, and I have numbers I can plug in for these things, right? So rather than express this as a sum, I can just say, look, with probability PU, I have unique elements, and my running time is 1/2 n squared minus n. Okay. Now with probability PL, I get a linear running time, and I'll just name that, right? I'll just say that's n minus 1, right? I'll just assume that my linear running time is n minus 1. I can modify that assumption later if I want to, but for now let's just stick with that. And then I know that with probability PC, I get a constant running time. Okay, and so here's my expression, right? So now this is something I can analyze, right? I can actually do algebra on this, manipulate it around, and see what I get. All right, so what is this reduced to? So what I end up with is n squared times pu over 2, right? So there's an n squared term, so that's interesting, plus n, okay, times PL minus PU over 2, all right, plus PC minus PL. All right, so what do we have? What's the order of growth of this running time? Well, let's make the assumption, and this is, we need one more assumption to be able to analyze this. We're going to assume that all of our PU, PC, PL are constant in n, right? I'm not going to try to claim that this is the right assumption to make, but for now, to make the math tractable, we're going to make this assumption. And so I'm just going to write this because this is actually a critically important assumption. We're going to assume that PU, PL, and PC are constant in n. Okay, so if I've made that assumption, then what do I get? Well, I get that if PU is greater than 0, then the average case running time is quadratic. Okay, so if PU is greater than 0, then T average of n is big theta of n squared. Right? Why is that? It's because I would have then a non-zero coefficient on this n squared term. Okay? And notice that this wipes out PC, this wipes out PL, right? The only thing that ends up mattering is that there's a quadratic term in the average case expression here. That there's a non-zero probability that I'll find a quadratic running time input. That's all that it takes to get me quadratic running time. And to be very precise, the thing that matters here is that the probability of my quadratic running times is independent of n. Whether that's a good assumption or not, I will leave to you to chew on. Whether it's a good assumption or not does actually impact this. However, under that assumption, my average case running time is quadratic. And note that it doesn't matter what PU is, right? So the one question we could ask is, what if PC is 0.9999, right? So 4 nines is a lot of 9s, right? So it's very, very likely that the first 2 elements in the array are equal. So what if this and then what, let's just let PL equals 0, because who cares about the linear cost? Because let's try to cook this thing as much as we can to give us a fast running time. And then PU is, 1 minus 0.999. So PU is then, I'm going to get the number of zeros wrong. There we go, 0001, right? So what if this is the case? Well, then the T average case of n is 0.0001 n squared divided by 2 plus just PC 0.9999. And, you know, it'll take a large input to be able to see this n squared show up. But this 2 is big theta of n squared. Okay. So the reason I go through this example is that sometimes what you can find is that under reasonable assumptions, or at least assumptions that appear to be reasonable, the average case running time is just as bad as the worst case running time, right? So this should be your initial takeaway, that having an average case running time equal to the worst case running time is not unheard of. It's not necessarily uncommon, but you know, sometimes the particular statistics of your input space don't matter a whole lot, right? That you're still going to kind of inherit this worst case running time for your average. And the question is this the whole story, right? And the answer is not quite. So let's just leave this video with a but wait, and pick it up again in the next video to talk about what other assumptions might lead to here.